So this week, lecture 3, we're going to talk about the driveline and tyres and tyre forces. Talk about the vehicle driveline first off, okay, and then talk about the tyre forces. What do we mean by vehicle driveline? Well, basically that's the driveline of getting power and torque from the engine through the driveline to the wheels at the other end. Okay. And so obviously the engine, this is a conventional IC engine vehicle. You can see connected to the engine with the clutch, okay. Power transfers through the clutch to the transmission, which is a gearbox essentially, okay. And then depending on, this is a rear wheel drive car, that transmission will then transfer to a prop shaft, which will then be the final drive, which is where the differential is, and that gets split along drive shafts to the wheels of the final.
So just a power track?
This is the power track, yeah, essentially. Now, sometimes things can move around. Some vehicles, they move the prop shaft into here, okay, or here even, where we have what's known as a transaxle transmission, where the gearbox is actually at the back of the car. And like I said, if you've got a front wheel drive car, this thing is actually completely gone because the final drive will be built into the transmission. But essentially that's the process for most cars. Clearly, if you've got a four-wheel drive car, then you've got a prop shaft going front and one going the other direction, so there'll be probably a transfer case in here as well. We'll split the torque between the front and the back. We'll come to the clutch and stuff. We're going to base it just on this process. This is like a conventional rear-wheel drive car, and so we can break these things into sort of individual bits. So you've got the engine here, okay. So this is the crankshaft of the engine. And the engine will produce torque, which we call T, E, okay. The transmission, okay, that torque is going to be transferred. There'll be a torque associated with the transmission, and then the torque associated with the drive shaft. These things are obviously interconnected because there'll be gear ratios between these things. Okay, so obviously if this is geared down, then the torque will go up, and then again, so on again. Okay, and then there'll be that's your differential, and there'll be a torque in the axle, and clearly the torque is going to be the force times the radius of the wheel. So those things are related as well. Okay, Fx being the tractive force that we covered a couple of weeks ago, and we called it Ft perhaps last week, or the week before last. Here we're calling it Fx because the x is the direction the vehicle travel. Okay. But like I said, there's a relationship between all this stuff. Okay, so let's have a look at some of the sums. Okay, so that the torque delivered through the clutch, okay, is going to be the torque in the engine, okay, multiplied by this is angular acceleration, okay, or the sum of all the torques equals I times alpha, okay. That's Newton's second law, but it's a rotational sense. We've got the inertia of the engine times by the acceleration of the engine. It's going to be the torque, and then it's going to be the torque in the system. Okay, and obviously the torque in the engine and the torque in the clutch is equal to the torque in the engine minus that acceleration. Clearly, if the engine's at a constant speed, alpha is 0, so the torque in the clutch is going to be the same as the torque produced by the engine. And that ratio is 1 to 1, so there's no gear ratios going on there. Okay. So that's the torque generated by the engine, TE, and then you've got the inertia of the engine and the flywheel, okay, times by the acceleration. Okay. And so, like I said, if the engine's not accelerating to the constant speed, then the torque in the clutch will be the same as the torque in the engine. Okay. That's straightforward, we can follow that. Now, the torque delivered to the drive shaft, okay, is going to be that torque in the clutch, okay. So this is the drive shaft, okay. We've got the inertia of the transmission, the acceleration of the engine, and the torque in the clutch. And that's multiplied by our gear ratio. Okay, because what's coming out the back of the gearbox is going to be that torque that's going into the gearbox, okay, times by the gear ratio. And that torque in the clutch is there. So that's the clutch torque, there's the inertia of the transmission, and that's the angular acceleration of the engine. Okay. and then you've got on the end there your gear ratio of the transmission. Okay, so we've gone from the torque in the engine through the clutch. Okay, so that's like I say this term here. Okay, and then we've got the torque going onto the drive shaft. So the torque of the axles, okay, is going through the final drive. Okay, so again, so we've got the torque in the drive shafts that we had in the previous equation. Okay, then you've got the inertia of the drive shaft and the angular acceleration of the drive shaft. Okay, going through the final drive gear ratio. Okay, and that torque at the axles equals your torque at the rear wheel times by the radius of the rear wheel, and then you've obviously got the inertia of the wheel and the acceleration of the wheel. Okay, so you can add all these things up and you end up getting a relationship between axle torque and the tractive force. Now, like I said, what you can do is you can substitute all those T, E, T, D, and T, C's into that equation. You end up getting something that's quite complicated. So, angular acceleration of the drive shaft, we've got the angular acceleration of the wheels times by the final drive. Okay, and then we also know that alpha D is going to be the transmission ratio times by the alpha E, okay, which is the engine. So you see the relationship between those things. And so you can relate this and this. If you substitute this in here, you end up with NTNF, which is going to be your two gear ratios multiplied together. So I've called that NTF, okay, which is your ratio between the engine speed and the wheel speed. In this case, engine acceleration and your wheel acceleration. So that's your total gear ratio from the front, from the engine all the way to the wheels. Okay. So NTF being the two gear ratios multiplied together. Okay. That's your gear ratio in the gearbox, and then you have a final drive. Okay. Alpha W is the angular acceleration of the wheels, and alpha D is the angular acceleration of the drive shafts, and the alpha E is of the engine. Okay. So, we're going to work out after quite a lot of sums, but obviously you can refer to these slides and follow along. What fx is based upon all these different things. Okay. Okay, so we've got the axle torque. Okay. Which we know is the drive shaft torque minus I D alpha D, okay, times by the final drive ratio. And we know that axle torque TA is Fx minus I W alpha D. Okay. Now we can rearrange that, putting Fx on one side, and then if you put Fx on one side, you've got this term minus this term. So that's our tractive force times by the radius. Okay, clearly you could divide that by R and you end up getting Fx, but in terms of T, the torque in the drive shafts. Okay, but what we actually want is that to be torque in the engine. Okay, with all the other terms thrown in. Okay, so multiply through by NF here, we get NFTD. Okay, minus ID alpha D times by NF. Now we also know that TD is the torque in the clutch minus the inertia in the transmission and the acceleration in the engine times by the transmission ratio. Okay, and alpha D was NF times by alpha omega. So the acceleration of the drive shaft is the gear ratio of the final drive times by the acceleration of the wheels. Okay, so that's these two terms in here. So you can multiply that out. Okay, so we've stuck those things in here. There's our term we put into here. Okay, and this is the term we put into here. Okay. So you get NF squared as your NT times your NF, so that's NTF. Okay. And again, no, the acceleration of the engine and the acceleration of the wheels is just NTF alpha E. Okay. So that's your term in here. Okay, so there's our term in here. Pop that into there. Okay. There's an NTF, there's an NTF as well. Okay, and then just go through what we had. Torque in the clutch, the engine torque minus the inertia, acceleration of the engine. So again, we stick that into here. Okay. You've got an NTF here, an NTF squared there. And you keep going through. So that's what we've got here. So we multiply this through to get this equation, which is this equation, okay? Divide everything by R and you get fx being this term here. Now, this thing we've seen before. If you remember back from chapter 2, we had an efficiency in there. Okay, back in lecture 2, we had FT, which was torque in the engine, okay? Times by the gear ratio, which is called NTF here, times the efficiency. And so basically that equals this equation, except obviously we start with the total drive efficiency on it. You end up getting an equation for the tractive force. Okay. Now I know there's lots of algebraic manipulation there, and like I said, you can download the slides after this session and you can follow that through. But basically, last week we came up with the equation of this one. Okay. Now the complicated factor here is we've got a bunch of inertia. Okay? If the vehicle's accelerating, okay, this term is 0, so that second term drops out. But when you're accelerating the vehicle, there's all these inertias you have to take into account for that to make for that to be an impact. Okay, so that's basically what this derivation is going through. You don't need to remember the derivation. I won't ask you to do that at all. But it's just understanding that, at a constant speed, that's the torque in the engine requires you to produce a certain tractive force. That tractive force obviously has to overcome all those resistances that we talked about last week. Okay, but if you want the vehicle to accelerate from a certain, so this so the tractive force, this tractive force needs to increase. You need to include these inertias in the engine, okay, and the transmission of the drive shaft. And the wheels, okay, and that's what if you look at performance cars and performance engines and stuff, they've got very low inertias, okay, the inertia of the engine, and if you think about, I don't know, aware of the Carrera GT, had a very light flywheel, well, that's that inertia there, okay. Clearly, if your wheels are heavy, you've got large unsprung mass, okay, but that's your inertia of the wheels. And the lighter wheels, you also reduce those things, so it reduces the necessary torque to have a certain acceleration, or you get greater acceleration with a given amount of torque in the engine. Okay. So, like I said, these inertias make a difference. And obviously, your gear ratios will also make a difference as well. But those factors are squared. Okay, so they make a difference. That makes sense. Okay, so like I said, it's really sort of being familiar, I guess, with the final thing. That's what we've seen that last week. Lecture 2, okay? You've got your efficiency times by your gear ratio of the complete transmission from the gearbox and the final drive and your torque of the engine divided by the wheel radius R, okay? It's going to be your Fx at a constant speed. If you've got acceleration, you need to take into account the inertias of those things. Okay, so that was just driveline, okay? Just a bit of sums, a bit of mathematics. And algebra just to rearrange to get that final equation, okay? But like I said, I'm not going to ask you to derive that, and I'm sure some of you followed, but many of you, so it's okay.